The Google Classroom grade, though, is what dings you if you don't have it done when you should. Okay, here we go. Number 4, vertical translation had something to do with D, right? Or sinusoidal axis or something like that. Number 12, your period was 3 pi, 2 pi over b. B was 2 and 3. It was 2/3, like we saw yesterday, which is multiplied by the reciprocal. Then the amplitude pause. Did you make it a positive number? Amplitude is always absolute value. The negative is what flips the curve to go a different direction. Instead of starting at the top, it will start at the bottom. But the amplitude is still up 1, down 1. That doesn't change with the negative. So amplitude, always positive. 18, kind of similar, 2 pi over b, or 2 pi times the reciprocal of b. 20 in amplitude, 2/3. Number 20, you were just looking at it the old-fashioned way and being like, hey, if there's an addition on the inside, isn't that a horizontal shift left? Perfect. How many units? Pi. Sorry, the answer key had a little bit of a typo. Just ignore the F. Just ignore him. Just pi units to the left. You guys are my ones that like it warm, right? Sorry, it's stuffy to me, but that's all right. I'm good. Oh, and right now I was like, Lauren, I don't know what to do. We're going to come back to 34 because he was nasty. Is that okay? 34 had like 2 different graphs. We'll come back to him in a second. Why don't we try number 44? He was a little bit more basic. Actually, he was super basic. How come? Didn't he still go up 1, down 1 like normal because nothing changed? Didn't he stay around the x-axis because nothing changed? Yeah. Sinusoid was 0, amplitude was 1. Sine start in the middle, no big deal. But where did he end? He ended at pi over 2. Now, quick heads up. I'm hoping that none of you guys wrote all this stuff out. Because the book's like, ooh, we need to write the points of every single key point. I just say, give it to me in the graph. So pause. Can we double check that you guys labeled your graph properly? All right. For me, you wouldn't have stopped with the period. What would you have gone on to do? With a quarter. That's 1/4 of 2 pi. Oh, true. I didn't label all the other stuff. So D is equal to 0. A is equal to 1. My C over B was equal to 0. Huh? Oh, the C in cycles. Gracias. I thought you meant the C over B as in I didn't write it out. Too many C's in math, man. I almost did it again. There you go. But just in case anyone's confused, there we go. There's the C over B also. But what's my 1/4 cycles? What's 1? Ooh. Yeah, just pi over 8. Just multiply by 1/4. So what would my units have been? 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8. Boom, 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 boom. Dun, 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 dun. Hey, that's where they got all these crazy numbers from. So I wouldn't make you guys write out all the ordered pairs. I wouldn't make you actually give me the 1 pi over 8, 2 pi over 8, 3 pi over 8, pi over 2. With it. I want to see that you can graph them. I can tell them, like on the test, for instance, if you have somehow these little x's labeled, and if they're the right x's as far as the different points that you had. And from beginning to end, it needed to go pi over 2, which it did. And it needed to go by 1/8 to get your different key points along the way. And like Jordan was saying, it's really tricky to get these waves to look nice. And so if you mark down your key points, not only do you get points from me for knowing what's going on, but you also have your wave nice and neat. 68, wasn't that a calculator? Just seeing if you guys can put it in. Cool. Cool. Real quick, if this went horribly wrong, you were probably in degree mode. If it went horribly wrong, like it didn't look like a wave at all in Zoom Standard, because this is really close to Zoom Standard. I mean, yeah, they shrunk it down just a little bit, and they made this a little bit longer, but you should have seen most of it in Zoom Standard. as long as you were in radian mode. There was a pi over 3 in here, so the shifting was by a radian. If it was like minus 30 degrees, well then you better go degree mode. But pi over 3, that's shifting the angle by radians. Sorry if we didn't talk about that a lot in class, but radian mode would have been the best way to go. 76, what was going on? Were you guys going from a graph to an equation or something? Oh, but from a graph, right? Were you given that? Okay, I stole this, I think, from the book. So you were being given, well, just so that we can look at it. You were given a graph and you were trying to find the amplitude and the d? Yeah. So the amplitude was, wait a minute, -1. Amplitude is just 1, but if you're labeling what should actually go in here, why did they put a negative? It's reflected, yeah. So this one said there was no shift, and if there was no shift, what's weird about this guy? Cosine should start at the top. He starts at the... Oh, I need a negative because of that. The amplitude was 1, but I need a negative in there because my cosine got flipped. And d was, what's halfway between -2 and 4? -3. Do we have any other evens, guys? Oh, yep, a couple more. What were the directions on 82? The directions you're supposed to be writing, the directions you get points for, the directions that I'm allowed to take off points if you don't write. Awkward. What are the directions? Matthew. So what can we tell on a graph? What do we see on a graph when y1 equals y2? What are we finding? Careful, not amplitude. If we're graphing two different graphs and if we're seeing where they're equal, intersection points. Intersection points, right? Okay. This is rough. I'm like pulling it out of you. So, where are the intersection points? If you guys had used your calculator, wouldn't you have gotten 3.141592? Oh, and then negative 3.141592. Oh, okay. So you would have gotten decimals if you had used your intersect feature in your graphing calculator. Where's that intersect feature again? Second trace. Good, second trace. Graphing calculator handbook if you needed it. But some of you might have just been like, wait, I know when cosine's -1. No big deal. That's pi. But if you were following the directions, you were supposed to graph in zoom standard-ish with radian mode and then say, hey, look, intersection. Hey, look, intersection. Guess what? It's pi. Guess what? It's -pi. Anyway, 86, you can see you were filling in once again to get the equation. And number 90. Number 90 was all about bridges. Did you guys figure it out? I can zoom in just a little bit because I know it's really small. For letter A, they were just asking how long, and how long is period. They're asking how long is period. So therefore, you could have just taken your 2 pi over b, which would have been 5 pi over 3. Multiply by the reciprocal, the pi's cancel, 2 and 3 is 6, and it's over 5. That was all based on the wording, how long. You wanted to find the period. But this guy, I think it brought in a new vocab that we didn't talk about. Was this one frequency? You guys should be able to see it. On number 90, brought in, oh, they didn't actually say the word though. They just said find the number of heartbeats per minute. So letter A was the period, letter B was the number of heartbeats per minute. Well, that's like a bridge, heartbeats over minutes. But what was this measured in? P is blood pressure per or in time t seconds. So how do we do heartbeats per minute if we have the blood pressure in seconds? So then, when you guys, nope, that's not the issues. There we go. And say it's a little tricky because from this equation, it would have been really hard, but from the period, it was actually easier. So we weren't going from the blood pressure straight to the heartbeats per minute. It was actually easier to do the period. And the period says, hey, it takes 6.5 seconds for 1 heartbeat. And so that's what you needed to start with. Without that, you would have been really lost. But this period means 1 cycle, and 1 cycle, with the blood pressure, 1 cycle is a heartbeat. So that's probably like the scientific fact that some of you guys might have been confused about. So that's those 6/5 seconds was how long it took for 1 heartbeat. So now that we have heartbeat per seconds, you guys know from Mrs. Leon, right? You got to get rid of the seconds and get minutes to get heartbeat per minute. So build a quick little bridge. Seconds are gone. When we do 60 over 6/5, we end up with 50 heartbeats per minute. So sorry, there was a quick little scientific fact in between there if you didn't know how blood pressure worked and what you exactly found with the period. The period of the blood pressure tells us how fast every heartbeat is. And you guys have been to like physicals and stuff where they're like holding and then the blood pressure cuff is on and they're trying to take your blood pressure and figure out your, okay, there you go. No, it doesn't. Hold on. Joe, I'm not saying P equals heartbeat, right? I'm saying the period of the blood pressure is how long 1 heartbeat. Okay, go ahead and write me an essay about it. It needs to be 2 pages, and then I'll go ahead and consider what you're saying, okay? Let's go ahead and go back, guys, to number 34. And if you want to gather information from Mrs. Johnson or Mrs. Leon, that would be awesome, and we could, as a class, learn about it. But for right now, we need to keep on going with math. So number 34. Guys, why was this one hard? Yeah, it asks you to do 2 graphs in one, and that's nasty. Like as Jordan and I were saying a little bit ago, it's hard enough sometimes to get one to look nice, right? So they were actually asking us to do 2 different ones and then compare the 2, which is why it got a little bit messy. And there's a lot of information on this screen. So I'm going to actually go ahead and first of all ask you guys, how many of you guys admit you have a question on 34? Like you're like, okay, so at least like 4 or 5 of you. And I would go ahead and ask how many of you guys actually tried homework, etc. But for right now, that's just going to be 34. Did I only give you 1 in this section, or did I give you a couple? Of sketching, more than 1. Okay, so I gave you 1 odd. And guys, do you ever realize that there's a method to madness? Why would I give you an odd before the even? And get an idea of what they wanted. Does that make sense? There's a purpose. And so if it's like, you don't check the back of the book until the very, very end of homework, or you don't check count until the very, very end of homework, if you're getting really frustrated on evens later on in sections, maybe you should have like stuck with the odd, figured out the odd, played with the odd first. Just a little bit. Okay, so this guy. The reason why it wasn't meant to be really, really bad, I could show you the answer key and you guys can scribble down the answers. That's not the point. The point is to understand. What changed with F? Because you're supposed to, I think, graph F, graph G, and then talk about how they're related. It's the long story short. And it says 2 periods of each. Okay. Are either of them vertically shifted? How high, how low? So I can automatically get F all set up, ready to go. So I'm going to have an amplitude of 2. And I'm going to have a period of 2 pi over 2. And I heard one of you guys say pi. You were totally correct. Now, I'm not going to really mess with my graph yet because I have to fit this guy in too. So if I start putting tick marks, it might mess me all up. Does that make sense? So I'm going to go ahead and think about G and be like, okay, well, number 1, G has been flipped. So he has a vertical flip, which means he's starting on the bottom. His amplitude is A. Sorry, well, duh. His amplitude is 1. So he's only half as high. And then what's his period? 2 pi over 4, right? Which will be 1/2. Even shrunk down more than this guy is. Now that I have all my clues, just for sake of illustration, now let's think about our graph. So now that I know that this guy goes up 2 and this guy goes up 1, I know that when I put my tick marks, I'm going to be totally fine. Because one guy is going to be cycling in here, one guy is going to be cycling in there. I have this guy going pi, which maybe I should put here, except that guy's only going pi over 2. Maybe I'll put pi way over here. Then I can put pi over 2 here. My quarter cycles, what are those going to be? Good. But what are my quarter cycles going to be for this guy? So I think I want to go by 8th pies, which is a little bit awkward, but I can cut that guy in half, pi over 4, and then that in half again, pi over 8ths. Cut that guy in half, that would be a 3/4. Cut that guy in half, 3/8. So now I'll go ahead and say, all right, let's do f. I'm going to make them red just to make it stand out. Cosine starts at the top. Every pi over 4, so he's going to jump 2 tick marks. He's going to be in the middle, then in the bottom, then back in the middle, then at the top. He's finishing in pi. He's going up 2, going down 2. 2 cycles would technically, okay, I'm going to be really imprecise. I could put my guidelines and all that jazz, but basically it goes over there the same amount, right? How am I going to graph the bottom guy, though? Why start in the bottom? Oh, that's right. So here? Why? Oh, so he's going to start here. So he's only going between 1 and -1. He's going to start down on the bottom because there was that vertical flip. Now, where's his next point going to be? Oh, so he's going to hit here. And then here. Oh, that's weird. They intersect. And then here. And then here. And then back. I can actually get, I think, 2 just by... Oh, those were not very evenly spaced. Oh, well. So then what's the book doing when it does all this nasty, like, wording stuff? Hey, you have this one going up 2, down 2, a normal at the top, and then cycling through. This guy starting down at the bottom of his 1, -1, and then finishing twice as long. It's just saying, hey, guess what? This is how they're related. G is half the height of F, and G is going to finish in half the time of F. That's basically what the relationship is. G is half as high, and G is going to finish in half the time. This period is half the distance. Okay, 34 is nasty. I apologize. The answer key made it look worse than it really, really was. And depending on how well you guys had gotten at your waves, it might have taken you longer. You might have had all these little guidelines. It might have been better to color code, etc. But the long story short, they just wanted you to put them together and be like, oh, hey, okay, so one's taller, the other one's going quicker. Jordan, what's up, kid? Yes, you may. Any other questions on evens or odds from homework? We haven't gone over odds at all. Any places you guys got stuck? Any question marks you need to fill in before the test? Yeah. 93. Anything else besides 93? Okay. If you guys don't have any questions, you can be having 93 like just open and available to reference, but you can also be getting your notes out because we're going to go play with those sinusoids. No, we're out of the sinusoid section. With the cosecants and secants. Actually, you know what? I think I have 93. No, I don't. Let's go grab them, though. The Ferris wheel problem is kind of like the sinusoid problem for the blood pressure, and that's just trying to give you like a real-life example of something that moves in a wave-like fashion. And a Ferris wheel is kind of like the pendulum in that it's not really like a wave in your head, as far as like, that's not a wave, but it actually will look like a wave when you graph how high you are off the ground. Because if you guys think about it, and the function kind of tells it too, if you go up 53, and then 50, that would bring us down to 3, and that would go up to, what, like 103. The Ferris wheel cycles around a middle point, like an axis, the circle, right? And then you go so low to the ground, but not quite on the ground, else that would be the ground. So when you're on the edge, you're going to be at a height of 3, and then a height of 53, and a height of 103, and then a height of 53, and then a height of 3, and then a height of 53, and then a height of 103, and everywhere in between. Yeah, you graph like how high you are from the ground with respect to time. Now, cosine would be good if you were getting in at the bottom of the Ferris wheel, right? Because you can start down and be like, okay, you're at 3, and now up, going up high and then down low, and then up high and then down low. Yeah, but you're going in. This one actually puts it in a model of sine. So what must be weird is they must actually have like the platform, like you go up the stairs to the platform and you get in. Oh, you can't see that, can you? They must have like stairs that you go up and then you get in the Ferris wheel here, and so the Ferris wheel goes this way and then the ground's down here, which is weird. Who would make a Ferris wheel like that? At California Adventure, you totally get at the bottom, right? Which should have been a negative cosine curve. Yeah, right? You'd have to, well, they're always stairs at amusement parks, so I guess they're like, whatever. Oh, yeah, because they actually have it kind of like into the ground when you get in. I wonder if there's like a safety thing as to why they'd want it that way instead of like you get in. Yeah, you don't want to fall through the gap. Okay, so this Ferris wheel, whoever made it, I don't know, maybe it's somewhere in Europe and so it was made a long time ago. Think about it that way. But they have the Ferris wheel, you get in here and then you're cycling around. Because you're going up, sine goes up first, a positive sign. So you must be spinning this direction as well as you go around. But long story short, doesn't A just say, hey, do you know how to do period? I know how to do period. 2 pi over who? Who is B? Pi over 10. Good. So 2 pi over 10 is going to equal 2 pi times 10 over pi, which ends up being 20. What does that period mean, though? 20 seconds is how long it takes you to complete 1 revolution, to complete 1 all the way around for the ride. Because that's going to be your top, middle, bottom, middle, 1 cycle. Yeah. Maybe it's a really small Ferris wheel? I don't know. Well, it's not small if it's 53 and 50. Anyway. Yeah. Well, I was thinking if it was a small circle, like 20 seconds isn't a big deal. Like, yay, 20 seconds, right? But if it's... Anyway. Coming back. Find the amplitude of the model. What does the amplitude... Wait, amplitude? Oh, that's easy. You guys see it, right? What does that mean? The radius of the circle is 50, or you could say the diameter top to bottom is... Technically, it tells you both, right? So it tells you the radius. Yes, it's how high, how low the wave goes, but it's not really a wave. It's a circle just moving in a wave-like pattern when, as Joe graph the height with respect to time. And then letter C says, use the graphing utility to graph 1 cycle. Isn't it? Come on, guys, we can do this, right? Dun, 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 dun. I mean, use your grapher and get it in there and make it look all nice and pretty and change your window. Or just not have to use your grapher at all. Does that make sense, Priscilla? Cool. All right, cool kids. Let's go do some secants and cosecants. All right, secants and cosecants. There was one thing I didn't talk about in detail yesterday because I was introducing this in, 3 minutes at the end of class, I'm pretty sure. There was one big thing I did not talk about with cosecant and secant. Said they bounce off. Joe mentioned that another way of thinking about it is cutting the sine cosine wave and peeling it away. That would be another way of thinking about it. But we'll see that in a second. What I didn't get to talk about was reviewing the unit circle to basically find the vertical asymptotes. Because whenever secant is undefined, it's going to have vertical asymptotes. And whenever cosecant is undefined, it's going to have vertical asymptotes. But the reason why I put review here is because we know who cosecant is. Cosecant is 1 over who, guys? Sine. And secant is 1 over who? So if we were to, just for sake of keeping this nice and organized, if we were to think about sine and think about cosine in relationship to cosecant and secant, we could actually figure out when the vertical asymptotes will happen because they're going to happen when the bottom equals what? Vertical asymptotes, they're domain problems. Functions not existing. What would make a 1 over not exist? 0. Ah, so when sine equals 0, then this guy is going to have vertical asymptotes. Exactly. When does sine? 1, 2, 3, sine counts up. So sine equals 0. when x is 0, right? Which is going to happen at, who are those two angles? And a lot more, because you can keep on spinning like a Ferris wheel. So maybe 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. All the pi's. All the pi's. When's cosine going to not exist? Good, good, good. The other one, when y is 0. Oh, I switched them. Oh my goodness. What is wrong with me? Yeah. You guys were probably looking at me and being like, she's crazy. Or, it's great. I don't know my unit circle either. Okay. Either way. Sine is when y equals 0, which was still at 0 in pi. We were right. 1, 2, 3. Sine counts up. Cosine 3, 2, 1. Cosine counts down. So we can say pi over 2, 3 pi over 2. Or if you're on a Ferris wheel and you keep spinning, 5 pi over 2, 7 pi over 2, 9 pi over 2. So we could memorize that. Does that sound fun, though? Kind of? Okay. For those of you that like to memorize, do that. For those of you that don't like to memorize, didn't we just say cosecant is going to have vertical asymptotes? Didn't we just say secant is going to have vertical asymptotes at the zeros of cosine? You saw enough of this to realize that we're going to be using the sine curve for cosecant and the cosine curve for secant. So if we have the sine and cosine curve, guess what we can make at the zeros without even thinking about it? We can make the vertical asymptotes at the zeros. So the long story short of all of this is we're going to put the vertical asymptotes at the, this is going to get a little weird, the sinusoidal intercepts of sine or cosine. Now it depends, secant or cosecant. It depends. Secant looks at cosine, cosecant looks at sine. But besides the whole bouncy off thingamabob, the maxes and mins, we're going to meet up. Or I think in honors this year I said me too. For cosecant or secant, the maxes and mins are like, me too, but I'm bouncing off. Me too, but I'm bouncing off. But in between, whenever the sine or cosine has an x-intercept, or if that gets shifted, has a sinusoidal intercept, it intersects the middle of the wave, no big deal. It's always just going to be a vertical asymptote. So we don't actually have to memorize this, which is nice. Say it one more time, Joe. Function? Kind of. I guess we could kind of define it for like, he's thinking like different intervals, right? Like 0 to pi over 2 and pi over 2 to, yeah, we could kind of do that. Or I should say 0 to pi and pi to pi over 2. But just because of who this guy is, we don't even really need to write out like all these different pieces. We can just kind of know how it behaves and not have to worry about all the separations. Does that make sense? Kind of? Okay. Oh, yeah, let me zoom in the bottom. Sorry, I told you guys I would do that. So, if it's just plain old cosecant of x, you just take plain old sine of x, which goes from 0 to 2 pi, up 1, down 1, zoop, 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 and you say, okay, me too at the max, me too at the min, vertical asymptotes everywhere that the wave hits the middle, and then bounce, bounce, done. But once you have that, technically you can say, hey, the domain is everything but all the pi's. The range is going to be forever high, starting at 1, and forever low, starting at -1, but not in between. It bounces off. So secant and cosecant actually will never equal those little fractions that sine and cosine do. And then the period is going to be 2 pi, just like it was for sine. And similarly, secant over here, he's the same idea, except everything's been shifted because it's a cosine curve instead, so the vertical asymptotes aren't at all the pi's, they're at all the odd pi over 2's. 1 pi over 2, 3 pi over 2, 5 pi over 2, skipping the even pi over 2's. Me too on the max, me too on the min, bounce, bounce with the vertical asymptotes. Done. The range, forever high, starting at 1, low, starting at -1. That's what's going on here. And the period says every 2 pi, just like cosine would be. So all of that can get us to, let's get a graph of cosecant secant. And that's what this page was about. Let's actually get one. But to get a graph of cosecant and secant, well, you got to start first with a sine or a cosine. So, yesterday, I already wrote out, like, well, if cosecant comes from sine, let's write this out as though it was a section 4.5 wave. Let's get the wave, let's make it dotted, and let's, me too, vertical asymptote, bounce, and we're done. So, where's my center? 0. I'm going to go ahead and just make this gray real fast. And then we can make it dotted. Okay, so 0. And then how high does it go? Good, so we have 1, we have 2. I have my period, which is just a 1, right? So I can say my period is just going to equal 2 pi over 1, which is just 2 pi. So my quarter cycles are still going to be just every pi over 2. But I have a shift, don't I? So maybe before I should have thought about my initial point. If you guys remember, initial point, my C over B is going to be negative, right? Minus. And sine starts in the middle, which is at 0. It's going to get a little awkward because I'm supposed to be going by pi over 2's. But I'm going to need to do pi over 4's. So I'm actually going to go by pi over 4's instead. And now for my sine, I have to start at negative pi over 4, start in the middle. I have to go pi over 2, which is 2 of these pi over 4's. I have to go 1, 2. The bottom. 2 to get back to the top. And I think I'll end up pi over 4, pi over 2, 3, pi over 4, pi over 4. If you guys were to put them together, you would end up with, did I get enough? Middle. Here you go. Pi over 4 plus pi over 2 plus 2 pi over 4 would be pi over 4, right? Plus 2 pi over 4. Oh, I never put my middle. I never put my middle. There we go. Something was weird. I was missing a point. There we go. Middle, bottom, middle. But wait a minute. That's sine. Who am I supposed to be getting? Cosecant. Oh, cosecant. Let's take that little sine guy and make him dotted. And say, me too at the max. Me too at the min. Vertical asymptote. Whenever it's going to hit the axis. And then bounce. Bounce. Okay. Today we were able to go over cosecants and secants. We're going to have a bell work at the very beginning of class tomorrow. Doing another cosecant or secant one with a bell work real quick in the back of our homework spiral. But then tomorrow we'll finish up with tangent and cotangent. No Google Classroom assignment is due tomorrow because we did the section backwards. So it's going to be hard for you to do homework because the cosecant secants are the easier one, but they're at the end of homework. So catch up in other classes tonight, and then we'll go ahead and learn tangents, cotangents tomorrow. Bye, guys.